So are all functions that you studied in algebra class differentiable? And the answer is no. I mean, here are some very interesting examples. You may have graphed this in algebra class, you may have not. If you have not graphed these before, they're not overly difficult. You just want to pick very careful numbers and be able to find ordered pairs that will help you understand these graphs. So maybe fill out this T-chart here of ordered pairs and you'll be on your way to really understand this. So if you graph these ordered pairs, I'm just going to do a quick sketch of this. This is definitely not to scale, if you're wondering. I will try, though. I will try to get it somewhat nice. So what happens here is that this looks like a seagull function. It looks like a function with, two wings of a seagull. What's happening is right here, if you zoom in, the point of tangency is actually vertical here. So if I highlight right here, the point of tangency is that, as you zoom in the origin, you're going to realize the tangent line here has a slope that is not defined. This is an undefined slope. In other words, it yields a picture of a vertical tangent line. So it yields a picture of a vertical tangent line, and we will say that for this function, f of x is not differentiable at a very specific number or a specific x value. F of x is not differentiable at x equals 0. So once again, we gain our intuition from graphing in an algebra class. Same thing here. If you're not familiar with graphing this function, you just got to pick some ordered pairs that will get you on your way. This is actually very similar to the previous example. Once again, you don't have to graph this to the perfect scale, so I'm going to go ahead and write NTS here. It's not going to be extremely accurate. It's just a good enough sketch to help you understand that not all functions are differentiable. And like I said, this is good enough. It looks like a cubic function, but turned sideways. And so once again, what happens as you zoom in, if I zoom in and made a magnified version of what's taking place near x equals 0, you're going to realize that you will have a vertical tangent line. And it will look like a tangent line with a slope that is undefined. So that is a vertical tangent. And once again, we could say this function is not differentiable at x equals 0. It is differentiable everywhere else, though. Now let's look at the last function. Here's a function that is piecewise. This is really a piecewise function. And we could see this just by illustration. But more importantly, the illustration is very interesting. It's an upside down V that is shifted up 2 units on the y-axis. And so there's a picture here. what happens is that you have a very sharp corner here. This is not smooth at all. So you have a point of tangency that wants to yield a slope like that, or I should say you should see a tangent line that will yield a slope of +1. You should also see another tangent line that will yield a slope of -1. So that can't happen. We can't have two different slopes at the same point of tangency. So here we have a corner. Once again, the function isn't smooth, so it's not differentiable. We could also conclude that this function is not continuous. I'm sorry, not differentiable at x equals 0. So here's a theorem that is more beneficial in understanding what is continuous. If f of x is differentiable at a specific x value, let's say that x value is a, then f of x is also continuous at a. Example 8, here's another true statement. If you haven't figured out this logic yet, think about this statement. If there is rain falling, then there are clouds. More importantly, the contrapositive is also true. If there are no clouds, then there is no rain falling, right? If you could imagine this, if you could imagine rain falling, well, where does rain come from? Rain must come from a cloud. However, if there's no rain, there can't be any clouds. So here's a theorem which is really the contrapositive of the theorem above. It's also logically very, very useful in the study of calculus. If f of x is not continuous at x equals a, then f of x is certainly not differentiable at a. You could actually draw your own pictures, but a really good picture would simply be any function that goes up in steps. So if you had a step function of some sort, or you have a jump discontinuity, you will know that that function is certainly not differentiable. Let's say that's 3. Let's say this is the up value of 4. This has an up value of 8. We can see that this function here is not differentiable at 3 because it's not continuous at x equals 3. So any disconnected function would be not differentiable at that disconnection. And a very common example in physics, why are we studying derivative functions? Well, if you ever have this curiosity towards displacement and velocity and the derivative of velocity is really the acceleration of an object. So if you ever have that curiosity, or if you ever been in a car, you know that the car has a position, and we could give it a position function. And the car, if it's moving, then it definitely has velocity. And if it decides to move faster from the previous moment, then it has something called acceleration, which is all related to the subject of calculus and the derivative function. So notice the derivative of the position function is actually called the velocity function. The derivative of the velocity function is actually called the acceleration function. And notice we could just rename things using this very special prime notation. However, this prime notation is very confusing. It's better to say this is the second derivative of the position function with respect to time. So if it helps, I could go ahead and write that. This is the second derivative of the position function. Second derivative of the position function with respect to time. That is a much better way to read this symbol right here.